Hello and welcome to another installment of MG Chemicals webinar series. Today we're going to be looking at our grease portfolio. We're going to break down the different subcategories we have within this portfolio. And we're going to dedicate a bit of time into understanding how to properly evaluate a grease. This is going to be a little different from some of the other products we've looked at so far. Products that are essentially polymers that cure to give a final finished properties. Greases sort of fall outside of that, being a dispersion. So they're dictated largely by the oils and fillers that they use. So we're going to go over that and look at our specialty grades. So with that, let's get started. So on the agenda for today, first thing we want to do is take a look at how do you make a grease. And that will sort of help us illustrate how greases are a different type of product if we compare them to some of the coatings and plastics that we've looked at in some of the other webinars. Then we're going to look at our specialty grease portfolio, starting with the lithium grease, and then moving on to the dielectric and electrically conductive greases, and then finally the thermally conductive greases, which actually has a lot of overlap from some of the other products that we've looked at, specifically some of the RTVs and the adhesives. And then finally, we're going to dedicate a bit of time to understanding grease properties. And again, they do differ quite a bit than the other materials that we've looked at to this point. So I want to go over some of the key ones that will help you sort of evaluate greases from evaluating the TDS so that you can get a better perspective of how that grease is expected to perform. Okay, so first thing, how do you make a grease? And a grease is actually a very simple thing to formulate and to produce. You start with a base oil, and this could be a synthetic oil or a silicone oil if you want enhanced thermal protection. And then under shearing force, you simply add different powder fillers to give it some of the properties that you want, whether you want high lubrication, whether you want it to be a dielectric grease, corrosion inhibition, thermal conductivity, whatever you want. So in that sense, it is different than some of the products that we've talked about in that we're not talking about polymer systems that are dissolved within a carrier. We are talking about powders that are dispersed within an oil. The powders simply act as thickening agents so that instead of a liquid, you end up with this paste type of consistency. Okay, so now let's start with our first subcategory, lithium grease. And this is about as simple and basic as it gets in terms of the greases. A lithium grease is basically a type of lubricating grease. So if you think about where you would use a lubricant, essentially it comes down to whenever there's friction from moving parts, you want a lubricant, and what that does is that reduces the friction, or as we call it, the coefficient of friction within two moving surfaces, so that they move a lot more smoothly together. So again, a lithium grease is a very simple compound. It's a combination of oil, lithium soap, and then typically some other additives that might give it enhanced lubrication, corrosion protection, things like that. So you'd use this again on moving parts, gears, pulleys, hinges, that sort of thing. Okay, and just to show you that we do have the one size in the 85 ml tube. So easy enough to dispense, you simply uncap it and dispense right out of it, similar to a tube of toothpaste. Next, we'll look at the dielectric grease. And dielectric greases are products that are very misunderstood. I've seen videos uploaded where people will apply these either by putting a big blob on a female connector, or they'll actually coat electric prongs with this grease, and that is not correct. This is a dielectric material, meaning it does not conduct electricity. So you cannot place it in a path where current is supposed to flow. And again, I'm talking specifically about a male-female type connection. But it is actually used there. I think it's just illustrated in the wrong context. So if you have something that's dielectric, you cannot put it where it would impede the flow of current, meaning you wouldn't put it on the prong or you wouldn't put it in the prong receptor. Instead, what it's used to do is it's dielectric, so it prevents arcing and it also prevents corrosion around these types of plugs. So instead of putting it on the plug, what you could do instead is you could simply put it around the female receptor. And then that in turn would prevent arcing between the two prongs. And it's also used again to seal out moisture, which can cause corrosion over time. You could also fill the female receptor. You just wouldn't fill where the prongs go into. Okay, so it's important that people understand how to use this, because again, I think it's pretty highly misunderstood how a dielectric grease is used in reality. So again, just looking at the different packaging options we have available in tubs and easy dispense cartridge and tubes. Now conversely, if we look at electrically conductive grease, here is a different story. Because again, we could use it to apply directly onto pins. But this first slide here illustrates how not to use it, in that you can't simply take in this case we're trying to illustrate a 16-pin connector, and put a blob through it and then just work it into the socket. And that's because what you don't want is you don't want two neighboring pins connected by this electrically conductive grease. Each pin is slotted to go in a specific receptor to carry the current to that source. And in the event that you were to simply blob it on and accidentally connect two neighboring pins together, you now have the opportunity to short it out. Okay, so you can apply it to pins. You just have to be very careful when you do so. So typically what I recommend when people ask is that they can simply put a tiny little dot on the tip and then just easily work that into the female receptor. But they have to do so very carefully. Again, you want to avoid accidentally bridging two circuits together. So correct application would be, okay, directly to put it onto a male prong. And that's used mainly if there's any kind of corrosion that can sort of circumnavigate that point, or if there's any irregularities between either the male or female surface, that you sort of bridge that with a conductive grease so that you have a steady flow of current. And again, available in multiple packaging sizes. We have multiple part numbers as well. So we have the 846, which is an electrically conductive grease. That's a lubricating grease. Conversely, the 847 carbon conductive assembly paste, we don't really mark it as a grease. It doesn't provide a whole lot of lubrication. This has a higher filler level, so it is more of a paste instead, meaning it really doesn't perform lubricating functions. And then the 8481 is a premium carbon conductive grease, and that's used and was formulated for enhanced corrosion protection. And again, available in larger tub sizes and tubes. Okay, so moving on, we're now going to look at the thermally conductive grease. And again, we've talked a lot about different kinds of materials, specifically the thermally conductive adhesives and the thermally conductive RTVs in the past. So this is not going to be anything new. And I've showed this exact slide on prior webinars. So again, if we're talking about trying to mate a thermally producing element, such as a CPU or a motherboard, to a heatsink element, we want to displace the air at that interface, and there's a few ways to do it. With a thermally conductive grease, we're looking at a non-permanent type of solution, meaning at any point we can rework it and make any necessary repairs if the grease were to dry out, for example. And by contrast, a thermally conductive adhesive is more of a permanent bond. So it can be removed, but it's quite difficult, whereas these thermally conductive greases, you simply unlatch it, wipe it away, and you can reapply new grease as you see fit. So we see this a lot with repair of personal computers, gaming consoles, things like that. Okay, and then again, several products available, sort of distinguished by their thermal conductivity values. So we have the 860, which is more of a low thermal conductivity grease. So that clocks in at about 0.7 watts per meter Kelvin. The 8616 super thermal grease 2, again, is more of a high thermal conductivity grease where we're getting close to 2 watts per meter Kelvin. And then the 8617 sort of comes in the middle of about 1, and that was designed, again, more around enhanced corrosion protection and things like that. We are starting to, in R&D, break new grounds in terms of higher thermal conductivity values, so we hope to start to achieve more in the range of 2.5 to upwards of 4 watts per meter Kelvin down the road. Available in, again, typical sizes include tubs, pails, cartridges, syringes, and tubes. Okay, so that covers the grease subcategory line. And now I just want to talk more generally into understanding grease properties. And again, these will deviate substantially from the different kinds of chemistries we've talked about in the past, the coatings, the plastics, because again, these materials are dispersions and they do not cure. So when we're talking about grease properties, we're talking more about the state of the product as sold, because again, that doesn't change with application. It doesn't cure and reach a final cured state. So it's important to sort of go back and understand what these properties mean. And so the first one we want to talk about is the oil separation, okay? And the oil separation is simply a test as to how much oil is going to separate if you subject that grease at a given temperature for a given amount of time. And on our TDS, we will actually specify in the footnote how we perform this test, what temperature we performed it at, and what was the time in which we ran the test. And so you simply isolate the grease in a closed vessel and then subject it to a given temperature for a given amount of time. And afterwards, you measure the amount of oil that has separated out of the grease. And you report that as a percentage of the starting weight. So you may see something like 3.4%, meaning the amount of weight lost from oil separation was 3.4% of the original weight. So again, that's run based on the ASTM D6184 standard. The second test we're going to look at is called the dropping point, and it's quite similar to the oil separation, but different in a way in that what we're looking for here is the temperature of the initial onslaught of oil separation. So once we see that oil has begun to separate out of the grease, we simply note the temperature at which it was done. So here we have sort of a stopper type of setup here. And again, it's insulated, and we heat it up, and we continue heating, noting the temperature. So we see the thermometer in the stopper there. And as soon as there's evidence that any oil has separated out of the grease, we stop the test. And they make some subsequent calculations, corrections, and they note the initial temperature where we start to see oil separate. So again, that's called the dropping point test, and that's run per ASTM 2265. And these will be shown in our technical data sheets. Okay, this next one's a little tricky to explain. It's called the water washout. And per the ASTM standard, it's typically run at two different temperatures. First being 38 degrees Celsius, and then the second one being 79 degrees Celsius. So we may report both temperatures, or we may just put that we only ran it at the one temperature. So in this setup, what you have is a bearing. And what you do is you fill the cavity of that bearing with the grease that you want to test. And from there you put it into your chamber, and the chamber will shoot a jet of water at a specified distance and a specified pressure. And again, you isolate the chamber so that you can control the temperature. So you're either going to run it at 38 or 79 degrees Celsius. And from there you continue to hit that bearing with the jet of water for 1 hour. And again, what you're measuring is the amount of grease that has washed out from that water pressure that you've subjected it to. So it's simply a before and after test. You take the weight of the grease before, you reweigh it after it's dried afterward, and you report the amount as a percentage of the original weight that has been washed out from the test condition. So that is called the water washout test, and the corresponding standard is the ASTM D1264. And the last one here we're going to look at is known as worked penetration. And broadly speaking, that is a measure of how soft or firm a grease is. Now typically with other materials we can look at something like the viscosity to sort of gauge how smooth, how thin a material is. You can do that with a grease, but it's a lot more difficult to get high precision and highly accurate results. So one of the ways to sort of standardize it is to run this worked penetration. And there's different kinds of work penetration. What we normally report is the work penetration of 60 strokes. So with that test, what they do is basically they will work a ram into the grease for 60 times, 60 cycles. And afterward, they remove the ram and they drop a cone into the grease. So by ramming the grease so many times, in fact, you're sort of working it. And it's a way to sort of loosen the grease up. And with the cone, you drop it at a very specified force, and you measure how far that cone is able to displace into the grease. So the softer the grease, the more that cone is going to displace, and conversely, the stiffer the grease, the less it's going to displace. So that's basically what you're gauging there. Typically, the lower the number, the stiffer the grease is. So it's called the work penetration test. And again, there's different variations, but we typically do the 60 half cycle testing, and that is ASTM D1403. And again, sometimes you'll see an NLGI rating, and that's another way to sort of gauge how soft a grease is. And again, that goes from 00 to 6, whereas the higher the number, the harder the substance. Okay, so with that, let's move on to some of the conclusions. So first conclusion, grease is prepared by dispersing powders into specialty oils. These products do not cure, unlike other MG products we have discussed. So we had to sort of look at, okay, this is a dispersion, and basically the product as sold is how it performs. There's no curing in which it changes properties or polymerizes or anything like that. So we sort of had to look at greases in a different perspective than we have with other products. We talk about lithium grease. It's a very generic grease that you've probably seen before, and it's simply designed to enhance lubrication between moving parts. Dielectric grease. Dielectric grease does not conduct electricity, is electrically isolating, okay? And that's meant to prevent arcing and corrosion because it is very hydrophobic. So again, we do not apply it directly on pins or female receptacles. We can apply it around them where it does not impede the flow of current. And again, the primary objective here is that we don't have overflow current arcing and we seal out the unit from any water, moisture, and corrosion. With the electrically conductive greases, these are electrically conductive in that they do carry a current. It is used to enhance electrical contact for plugs and irregular surfaces, or where the metal has corroded. Thermal grease, and again, this wasn't really a new idea because we've covered it quite a few times already with the adhesives and the RTVs. So it's used in the same way where we're looking to displace the air at the interface of a heat generating component and a heatsink. And again, since these products do not cure, we got to evaluate them in a different perspective. So we look at things like the dropping point, the water washout, the oil separation, and the work penetration. And that's going to give us an idea of how well that particular product will fit in terms of the environment it's up against. And that's really what a lot of these properties are used in order to help the customer gauge if they have the right product in mind. So with that, we are finished. I'd like to thank you for your attention. My name is Michael Strong. I am the Technical Support Manager. You can reach me at either of the email listed or my direct line is listed below, and I will now open the floor to any questions. Thank you. Okay, so thank you for your time. Do we have any questions now? Okay, it looks like the question panel is empty. So if there's no questions, that's fine. You have my contact information. If you can think of something later on, please feel free to contact me at any point, and I'll be happy to answer any of your questions. If not, have a great rest of the day. Thank you.